Welcome to Chem We Talk, a channel where we're not afraid to talk about any chemistry topic. In today's video, we'll discuss the difference between strong and weak bases, as well as go over examples of how to calculate the pH of solutions containing either a strong or a weak base. Some of the questions we're going to answer in today's video are: what is a base? Do you remember the autoionization of water? What is pOH? And what is the relationship between pOH and pH? What is the difference between strong and weak bases, and how do we calculate the pH of solutions containing either a strong base or a weak base, as well as what is percent ionization? There is another video in this channel that goes much more in depth over acid-base theories, but for this video we're just going to quick review on Arrhenius and Bronsted-Lowry definitions of a base. For Arrhenius, a base is any species that can increase the concentration of OH minus in solution. So for example, if you use NaOH, NaOH dissociates in water producing Na plus and OH minus, hence it is a base. Bronsted-Lowry has a different definition, and it's simply any species that can accept an H plus cation. So let's look at this example here where we have NH3 and water producing NH4 plus and OH minus. And we can see that the H2O can donate a hydrogen to an H3, which can accept the hydrogen, and because it accepts the hydrogen, it behaves as a base. And we can also see that NH3 in water increases the concentration of OH minus. So this example also fits the Arrhenius definition of acid and base. All right, for us to go and find out the relationship between pH and pOH, we need to go back into the autoionization of water reaction. So here basically we have water reacting with another water, and those are both liquids. That's going to be relevant because remember, liquids do not go into our equilibrium constant expressions. But we're going to have this water here in red donating its hydrogen to this water here in blue. So this water is going to behave as an acid. This one's going to behave as a base. And that's going to produce OH minus and H3O plus. And those are both ions that are aqueous. That's why it's called autoionization of water, which means that water is ionizing itself. All right, how would we calculate our K expression? It's just products over reactants, right? But in our case, our reactants are both liquids. So our K expression would simply be the product of our ions in the product side. So H3O plus at equilibrium, OH minus at equilibrium. And we know that at 25 degrees C, which are most problems at, we're going to have 1 times 10 to the negative 14. Let's just do some manipulation here in the math and see what we get. So first thing we're going to do is just going to be taking the negative log of everything. So simply I'm just going to write negative log on this side, negative log here, and negative log there. So we get negative log of Kw equals negative log of the product of H3O plus at equilibrium and OH minus at equilibrium, which is equals to the negative log of 1 times 10 to the negative 14. Just remember one of the properties of logs. If we have the log of a product, we can break apart into 2 logs by adding them together. So that's what we're going to do with this part here. We have the log of the product of H3O plus and log of OH minus. So we can separate those into the log of H3O plus the log of OH minus, but because we have the negative sign, we end up with negative log of H3O plus minus the log of OH minus. Okay. And we also know that in chemistry from the acid and base videos that any time we see P in this chapter, we're going to see that P equals negative log of something. So negative log of Kw, negative log of H3O plus, and negative log of OH minus, we can replace that by something. But just remember that H3O plus and H plus are the same thing as well. So let's just replace everything that has a negative log of by P. So negative log of Kw will become pKw, negative log of H3O plus, because H3O plus and H plus are the same, will become pH. And negative log of OH minus will become pOH, and we get the negative log of 10 to the minus 14 is just 14. So we get this relationship that's going to be very, very important for this part of the material, which is pKw equals pH plus pOH, that equals 14 at 25 degrees C. Okay, so let's look at some of the strong bases. Strong bases, like we saw in the example of the acid-base theories, we have NaOH as an example of a strong base that breaks apart producing Na plus and OH minus, and barium hydroxide, it's an example where we have barium 2 plus dissociating to also 2 OH minus. Be careful, differently than strong acids that had more than 1 proton, where we would only remove 1 proton. Here for bases, if you have 2 hydroxides, we will form 2 hydroxides. Okay? So let's look at this question here. Let's say that I had a solution that was 0.1 molar NaOH and one solution that was 0.1 molar barium hydroxide. If I drop those concentrations there and come back 5 minutes later, how many moles of NaOH and how many moles of barium hydroxide would I see in the solution? The answer is 0 for both of them. Because those are strong bases, as soon as those reach the solution, they will completely break apart, producing Na plus and OH minus, and Ba2 and 2OH minus. So we will not be able to see any NaOH or barium hydroxide staying together. Okay, so let's see how we actually calculate the pH for solutions containing strong bases. The first example was this NaOH solution. Okay, and we know that NaOH dissociates, producing Na plus and OH minus. And because NaOH is a strong base, we can assume that all the NaOH that was present will be converted into Na plus and OH minus. So if we had 0.1 molar NaOH, that will break apart, producing 0.1 molar of each because the ratio is 1 to 1. Okay, so if I want to calculate the pOH, which is simply the negative log of OH minus, we just take the negative log of 0.1, which equals 1. But if you're looking for the pH, we know from the previous slide that pH equals 14 minus pOH, which is going to be 13. Now going to the second example where I have barium hydroxide, this one's slightly different because now we have two hydroxides. It is still a strong base, so it's going to break apart completely, but for every one barium hydroxide, I'm going to produce one barium 2 plus and 2 OH minus. So if I start with 0.1 molar barium hydroxide, I'm going to produce 0.1 molar barium, but 0.2 molar OH minus, and that's what we're going to use to calculate pOH now. So pOH is simply the negative log of OH minus, so negative log of 0.2 becomes 0.7, and then pH is going to be simply 14 minus that and get 13.3. Okay, so be very careful with bases that have strong bases that have 2 hydroxide. Those would be barium, strontium, and calcium most commonly. Okay, so how do you memorize strong and weak bases? Most commonly, the strong bases that we're going to be using in general chemistry are going to be hydroxides formed by metals from group 1 and 2, with the exception of beryllium hydroxide and magnesium hydroxide, because those are not very soluble. So any of those in those two columns, with the exception of beryllium and magnesium, will be strong bases. So for example, lithium hydroxide, lithium's in group 1, it's a metal, okay, no hydrogen. And then calcium hydroxide is in group 2, and it's not beryllium or magnesium, so it's going to be a strong base. And then if you look at possible weak bases, iron hydroxide, iron is here in the middle of the table, so it's not group 1 or 2, so it's going to be a weak base. And magnesium hydroxide, it is in group 2, but it is one of the exceptions. Just want to make sure everyone's aware that this is not a comprehensive list, and there are other strong bases that are not listed. I'm just listing and telling you how to memorize the most common ones. Okay, now moving on to weak bases. The reaction is going to proceed very similarly, and we can use the Bronsted-Lowry definition. So in H3 in water, a base is going to accept the hydrogen from the acid, so it's going to produce NH4 plus and OH minus, so we can still see the OH minus being produced. And if we just use a general representation of a weak base, I can call it A minus, and this A minus can accept the hydrogen from the water, producing HA and OH minus. And one thing we can note already is that we have now a double arrow. So let's say that I have a 0.1 molar NH3 solution, which is a weak base, and I do the same thing as I did for the strong base. If I drop 0.1 molar NH3 and come back 5 minutes later, would I see any NH3 as a whole molecule? The answer is yes, there will be some NH3 present. But the question is, can you calculate how much NH3 will be present or how much OH minus will be produced? So what do we need to do to solve for the concentration of all the species in equilibrium and also solve for pOH and pH? And the answer is, for any weak species, we need to do an istable, and because we're dealing with bases, we will need to use Kb. Okay, so let's calculate now the pH of a solution of ammonia that is 0.1 molar. Okay, so let's just write down the reaction like we did in the previous slide. So we have an H3 react with H2O, because this is a base, it is accepting the hydrogen from H2O, producing H4 plus and OH minus. And we were given Kb. But remind ourselves what Kb is. Kb is just the concentration of NH4 plus at equilibrium times the concentration of OH minus at equilibrium divided by the concentration of NH3 plus at equilibrium. So for us to find out the concentrations at equilibrium, we need to write an istable. So we know that liquids do not go into istable, so we're just going to ignore that column. And the problem, we were given that we had 0.1 molar ammonium, so we put the 0.1 there. And nothing was said about NH4OH minus, so we're just going to assume it's 0. For the 0, we're just going to put a negative for reactants and positive sign for products. And then we look at the coefficients. It's like a 1. This one we ignore, 1 and 1. So we're going to do minus x and plus x for those two. And for the E row, we just read those two together. So it will be 0.1 minus x, x, and x. Okay. So we have our Kb expression. And now let's use the values from our table and substitute that. What is NH4 plus at equilibrium? That is x. OH minus at equilibrium is x. And H3 at equilibrium is 0.1 minus x. So we plug in everything there. And that should be equals to the Kb given in the problem. We're going to make an assumption here that x is going to be negligible, and we're going to check later and explain the conditions for it. But if we do that, we can just multiply 0.1 times that, becoming 1.8 times 10 negative 5 times 0.1 equals to x squared. X squared equals 1.8 times 10 negative 6. We take the square root, we get 0.0013. And once we go to our table, x corresponds to the concentration of OH minus. So if I take the negative log of x, we're going to get the pOH. Okay? But if the question was asking for pH, we just do pH equals 14 minus pOH, and you get that 14 minus 2.87, which was our pOH, is going to be equal to 11.13. All right, so we said we made an assumption, so we need to check the assumption here that x was negligible. So the way we do this is by looking at our final amount of OH minus that was produced and compared to our initial concentration of our base. And once we do this division multiplied by 100, if this number is less than 5%, we are generally safe. So we do this, we get 0.0013 divided by 0.1 times 100, get a 1.3%. So we are below 5%, so we should be good. If that's not the case, we're gonna need to use a quadratic equation. All right, so we're almost at the end. Let's just make a direct comparison between strong and weak bases. We saw that for a strong base, such as NaOH, it will break apart completely into Na plus and OH minus. So if you know the concentration of your base, initially you just take the negative log of that and you find your pOH. Just be careful with the number of OH minus present, right? This one has only one OH, so it's easy, just take the negative log of it. If there were two OHs, we need to multiply the number by 2 before taking the negative log of it. For a weak base, such as an H3, we will need to do an ice table and solve for x, and once you find x, you take the negative log of it to find pOH. But the main difference between a strong base and a weak base resides on its percent ionization, which is simply defined by the total amount of OH minus that is produced in relationship to the initial concentration of your base. So in this case, we had 0.1 molar NaOH solution to start with, and we produced 0.1 molar of OH minus. So once we do this, we can see 100%. So strong bases are going to be bases that will ionize or dissociate completely, so 100%. In the case of ammonia, we saw that our initial concentration of ammonia was 0.1, but only 0.0013 molar were converted. And when we do this calculation here, we get that only 1.3% is converted. So every 100 molecules of NH3, only 1.3 of those will produce OH minus. Okay? And if we were to calculate the pH, it would be just simply 14 minus pOH, and we get a pH of 13, and we get a pH of 11.13 here for the weak base. All right, so strong and weak bases differ by their percent ionization. For the same base concentration, strong base will have lower pOH, but they will have higher pH. All right, so in summary, pH is simply negative log of H3O plus, and pOH is the negative log of OH minus. pH plus pOH equals 14 only at 25 degrees C. The most common strong bases are the hydroxides of groups 1 and 2, except beryllium hydroxide and magnesium hydroxide, which are weak bases because they do not dissolve very well. For you to calculate the pH of strong bases, we simply take the negative log of the initial base concentration to calculate pOH, and you can do 14 minus pOH to find pH. Just be careful, some strong bases from group 2, such as calcium, strontium, or barium hydroxide, they have 2 OH minus per base, so we need to multiply the concentration by 2 before taking the negative log. And lastly, for weak bases, because they do not ionize completely, we need to use an ice table and Kb to calculate pOH first. And usually you can make an assumption that the X in your calculation will be negligible as long as the percent ionization is less than 5%. And once you do that, after you find X, you just take the negative log of that to find POH, and you can do pH equals 14 minus POH to solve for pH. Alright, thank you for watching. I hope this video was helpful. If you liked it, please share with your friends, colleagues, and lab mates, and don't forget to follow us on social media. Thank you. Bye.